live now. So.
Bad.
All right. Okay, so I think we're live now. This is the first time that I'm doing this live with all three of us here, and we're doing it not from my house, but we're doing it from the planetarium office back here, just so there is a more stable connection here, network connection. So hopefully we won't have all the freezing and lagging like you guys have experienced in our past streams. So we're going to try to move forward with more of our live streams here, especially with Astronomer here from the planetarium. All right, so today's theme is stars, and we have our PH students, Marcus Thomas and Cooper Dix, joining us again here this week. Before we get started with the questions, I just want to some things that we usually go over at the beginning of our live streams. We do have our trivia nights on Wednesday starting at 7 p.m. and we have our weekly Sky update on Saturday. We're not sure if it's going to be either a live stream or a pre-recorded show, but either way, you're going to see something at 2 o'clock on Saturday. And then again next week for Ask an Astronomer, we'll be doing it again. But our next theme, I believe, is going to be about cosmology and particle physics. So I believe it'll be.
It's going to be a vote between the two.
Pardon?
We're going to have to vote between those two. The public's going to vote.
We are voting between cosmology and particle physics. If we had both of those, then it would be pretty crazy. It would be too much. We got to save one for another week. Okay, so I believe we have our questions pulled up. We do have some questions that we can start off with. We did get a question earlier. Earlier this afternoon from Julie Seeley. So when you guys want to answer her question first, she's Julie Seeley from Facebook.
Can you read it to us?
Oh, yeah, I can read it to you. So she asked, can I see Neowise from Denton, Argyll area? And if so, what time is best?
Well, the biggest problem in the Denton, Argyll area is light pollution. Short answer, yes, you will probably see something, but it may not be as bright as if you were in a darker area. You might not be able to see the tail, but you will be able to see it tonight, and tomorrow night will be the peak. It'll be about 10 to 15 degrees above the horizon around 9 to 10 o'clock. So again, 10 to 15 degrees above the horizon, so right above the horizon, around 9 to 10 o'clock is when you should look out for it. And it'll be pretty obvious it's a comet.
Yeah, so it's it should be really close to the Big Dipper, right? It should be just like kind of below the Big Dipper. So if you know where the Big Dipper is, it's make sure you have a clear area where there's not very many tall trees, right?
Yes.
Yeah, ideally.
Especially trees that aren't 10 to 15 degrees above the horizon.
Right, that would make it much more difficult to see it.
Okay. I'm pulling up the question sheet now. For those of you, here's some behind the scenes. We have a Google Doc full of questions. That's the end of my behind the scenes. Thanks for coming to my TED Talk.
Yeah, which, if you guys have any questions during this time, if y'all want to just throw them in the Facebook chat, if you want to comment on the live stream, go ahead and just do that, and then we'll get those questions and hopefully get to them by the end of the stream.
You can also send us a fax with your questions. I don't know our fax number, and we are not in the office with our fax machine right now, so we won't get them for a while.
Right, so the answer is no to fax.
No faxes,
yeah.
Please.
I'm going to avoid faxes at all costs.
Unless you don't need a speedy response.
Right, of course. But okay, so I mean, let's go ahead and just dive into today's first topic, yeah? I mean, we're talking about the sun and the stars, and I believe Ashley's gone kind of pulled up for us a lovely diagram that basically all astronomers will know as the HR diagram. This basically talks about the life cycle of stars. If you follow this diagram, you'll know pretty much where we are at all times. It is the text is a little bit hard to see, maybe on the actual live stream itself, but if you actually go to the bottom right of this picture or this image, and then you follow it up to the very top left, that process right there, that's going to be called the main sequence. And the main sequence is where majority of stars live. It's where most everything is going to be happening, where as stars go through their life cycle, this is what they're going to be going through. And our sun is along the main sequence. And our sun, as special as it is to us, is a pretty normal star. There's nothing too crazy about our sun. If you can't see, the sun is essentially almost right in the middle, a little bit to the right of this graph, right before it breaks off into the giants and the supergiants. That's where our sun is. And Marcus, I don't know if you want to take it from here and have some words, but
yeah. Ashley, can you mute your mic? So the main sequence, this line you see right across that Cooper was talking about, this is where the most stable stars live. Stars spend probably 95 or to 99% of their lives in equilibrium. So they're born, they almost immediately take on the shape that they will stay at or the size they'll stay at for their entire life, and they'll move along this main sequence. And when I say stable, we'll probably come to this later. Stable means they're in equilibrium, which means the radiation pressure from the core there's fusion going on in the core, and that fusion puts off radiation, which puts pressure out. But then all the mass of the star produces gravitational pressure, which pushes in. And whenever the radiation pressure is equal to the force from the gravitational forces, you're in equilibrium. And stars that are redder and yellow, they'll be there for billions to tens of billions of years. But stars that are bluer up in the top left, they'll probably not last billions of years, order of hundreds of millions of years or less if they're big enough, because bigger stars have more gravitational force and they burn up their fuel quicker. They are not as stable. They burn to much heavier elements and they burn fast compared to the little stars that burn very slowly. So you can think of it like a little compact Prius. It burns fuel very slowly because it's small and it's lightweight and it has a small engine. And you can think of these giant blue stars as Hummers that get like 6 to 8 miles per gallon. They're giant engines making a lot of noise, pulling a lot of weight. They just burn up really quick. So,
and I'd like to say additionally on part of that, if you were to have a back of a napkin kind of definition of a star, it's basically any astronomical object that's fusing hydrogen to helium. And as they travel along the main sequence, they're using their hydrogen reserves to fuse that into helium, which has a very large amount of energy that's released that's, as Marcus pointed out, is able to kind of counteract that the gravitational pressure that's coming in. So the radiation pressure of that energy that they are producing is enough to actually hold off gravitational forces. So these are actually able to live for a long amount of time just fusing hydrogen into helium. But then as soon as you have burned up your entire hydrogen reserve, you are now entering a stage where you rapidly have to start burning up the rest of your chemicals, because in order to fuse and get enough pressure in order to resist gravity, you're going to have to continuously do that at a more and more rapid rate in order to not collapse in on itself, which we find as soon as you hit to iron, which basically, as we discussed a little bit last week, you basically will always fuse up to iron, and then at the point where you're at iron, then it's no longer energetically favorable for you to fuse, which leads us into a whole different discussion. Is once you run out of fuel, what's going to happen basically to that star?
Mm-hmm. So, and you can think about, I'm sorry, something just popped up on Facebook. So once you get past fusing hydrogen, it takes a lot more energy to fuse helium. And then it takes a lot more energy to fuse lithium, and then a lot more to fuse the heavier elements. So stars will very rapidly use up their fuel as they start forming heavier and heavier elements, just because it takes so much more energy to, well, what we call nucleosynthesis, to combine the nuclei of the smaller elements and create bigger ones. I lost my train of thought.
No, it's all good. But basically, whenever you run out of this energy, whenever you run out of this fuel, we end up with basically an iron blob. And to be completely honest, nobody has any clue what's happening after that point. What happens is you run out of that energy. We know that there is some type of collapse into the core because gravitationally, there's no more pressure for us to hold the star's structure together. And it collapses in on itself. And what the result is a supernovae. I'm sure you guys have seen rather pictures of supernova because they're very pretty.
We have pictures of those.
Yes, absolutely.
Yeah, Ashley, can you pull up slide 5, please?
And these supernova look gorgeous. And actually, it's where all of our elements that are any higher on the periodic table than iron, they come from these stars that have exploded and basically spit their elements out into the world. That's where the elements anywhere past that. If you've got, because that element.
Cooper, repeat that last sentence. Your audio cut out.
That element, if you have gold on your finger at all, that has come from supernova at some point, because these things do not get fused naturally in stars. They actually get produced from these supernovae. And basically, supernovae spit these elements out into the universe, and they somehow, one way, shape, or another, have found their way to Earth. But nonetheless, we have absolutely no idea what happens between the time that they stop fusing into iron and the time where they begin to collapse into itself and produce the supernovae. The processes there are just simply unknown, and basically most astronomers nowadays that study supernovae have had a better job of getting more accurate, more rapid results in terms of it is very difficult to catch a supernovae the second it happens out in the universe, because you just have to have that happenstance where you're looking at that particular area of the sky, and we also happen to have the right telescope looking at it, and there's so many factors that have to line up that we don't necessarily get to see the actual process take place. I don't know if Marcus, do you have anything to say on the old supernova?
Yeah, so for a lot of astronomical processes, what we do is we model them with computers. We write programs, putting in all the parameters, and we just tell the program, go, model this phenomenon. But with a supernova, that's incredibly difficult because we just don't have the computing power to model everything that's going on in a star. A star is 3 dimensions. It's got length, width, and height. Our computer models currently, they're pushing 1 dimension. Some of them are in 2 dimensions, but they're not that complex. And the reason we don't understand what's going on is because we just don't have the computing power to account for billions and trillions of particles inside of a star. So with short of direct observation in multiple wavelengths during the moments before, during, and after a supernova, we are not technologically in a place to model it and understand what's going on inside of it. Okay, so let's put a stop there, a pause on this. And do we have any questions from chat, Ashley?
Yeah, so we have a question from, someone named Cade. I think I know him. Yeah, so he asked, what is the biggest star?
Number 2. Next.
Oh, I forget. It's like Scuddy, I think it is called. It's like
what?
SCUTI. I think it's what it is.
I'm going to use.
And I think it's something on the terms of like 1,500 to 1,800 times the size of our sun, if I'm not mistaken.
So there's this special tool that's available to astronomers, not the general public. I'm going to use it. I just Googled what the largest star in the universe is.
Okay.
Scuddy, I don't know. I've never heard of that before.
I think
And
it
this
is.
article I pulled up is just too long. Oh, you're right, Cooper. It is Scuddy.
Hey, there we go.
30 times more massive than the sun. The radius is 1,700 times larger than the sun.
Okay. Yeah, I thought it was ridiculously larger than the sun. And this is what we would go to as the red supergiants. I mean, these things can get absolutely giant. I mean, it kind of gets lost in the numbers, but the true scale of all of these things. I mean, even the sun is so much larger than the Earth, where we think, oh, the Earth is pretty large. If you were to travel to France, you'd be like, oh, this sucks because I have to take a giant plane flight because the Earth is huge. Well, guess what? The sun is a lot larger than that. And then here we are with Scuddy or Scooty. I don't know how it's pronounced, to be fair. But
Special Agent Dana Scully from the X-Files. That's how you
there we go.
Yes.
That's what it is. And that's even larger, and so we're dealing with these objects that are absolutely giant, and that is really an understatement. I wish there was a way to really make that hit home, but it's so hard to tell, or so hard to.
Yeah. So the picture that is up right there, so it's just a very, very small visual of how stars can get, but even it's showing the largest star here is Antares, which is the heart, or that red star in the heart of Scorpio. It's actually out right now in the summer. It's up after sunset, so you can see Antares yourself tonight if you want. But Antares right there is it's not that big. There's a lot of visuals that you can look up online to see the size comparison of stars, but this is actually very small, still small compared to Scully. Well, no, I mean Scully star. Yeah, so Betelgeuse is, if you remember, is famously in the armpit of Orion. Yeah, and Aldebaran is actually the eye of Taurus, the bull. So that's right next to Orion. When you see those two red stars in the winter in Orion and Aldebaran, or in Taurus, those are those two stars. That's the comparison right there. And then our sun is you can't even see it on the screen, but it's just one pixel right there. Yeah, and yeah, that's all I have to say about that. There's not very. This isn't. This is kind of a good representation of the star comparisons, but.
Right, and to comment on one of the stars that was actually present here in Betelgeuse, recently, I say recently, I mean within the past few months, Betelgeuse has actually dimmed over time. For whatever reason, we're not entirely positive. There's a few theories behind it. Some people that are rather optimistic think that, hey, maybe we'll see a supernova in our time, which would be great, because I think that would be great to see in the sky. But other people have said that I think there's 3 cycles of Betelgeuse that we actually see, and one of them is something on the age of 3 days long. One of them's on 60 days.
Betelgeuse is a variable star, and variable stars go through periodic cycles where every so many years or days or decades or millennia, their brightness peaks and then it goes back down. It peaks and it goes back down. Betelgeuse has 3. I think one is on the scale of 3 days, one's on the scale of 600 days, and one's on the scale of 3 years. And some theorize that all 3 of those scales happen to line up at the same time, and the star dimmed a lot. My personal theory as an astronomer, I think that Cooper's butt floated in front of it and dimmed it significantly, because that is actually the largest star in the universe.
Right, of course. How could we forget the largest moon, as we would all say? No, yeah, really, I think more likely the variance of Betelgeuse is probably the result of the dimness that we're seeing. But if it was actually a supernova that would come to fruition, that would be great. I think it would be really interesting to see. I think we'd also be shot with a lot of particles, which would be cool. But
if it were to explode, we would see it in the sky. We'd see it during the daytime, bigger than this, probably as big as the sun for months.
Right. I mean, these things are absolutely insane. The supernovae. these explosions that would occur. And let's go in at least just one or two more of
let's
these.
Get some more questions. We actually have more questions coming in, or probably a lot faster. But hold on, let's see. We have one from Deborah Emmett. Oh, Emma.
Deborah.
Does a meteor glow?
It depends what your definition of glow is, I think.
Mm-hmm.
I believe, Deborah, the meteors generally glow in the infrared, but that's based off of the amount of dust that they accumulate around them. And by what I mean by glow is essentially like have such bright output. But if I'm not mistaken, and please correct me if you know better, Marcus, I do believe that they actually produce a lot of infrared radiation, which is what we would see in a lot of, depending on what telescope you're looking at. Granted, our eyes are some great telescopes, but they only see optical wavelengths, so we can't see that infrared glow. We would see them still bright in the sky as they burn up through our atmosphere, but in general, I don't believe they would actually particularly glow, as I don't believe they reflect a lot of optical light.
No. The reason that we see the streaks through the sky during a meteor shower is not necessarily because the meteors are flying through the sky, but a lot of the time it's because Earth is moving through a field of meteors. And Earth is moving, and they're streaking through the sky and sort of burning in our upper atmosphere. So we do see glow whenever they encounter something like an atmosphere, because they'll burn through particles in the atmosphere, or something like a comet, like Neowise. Neowise has a tail. That tail is just a bunch of dirty gas and dust. And that gas and dust absorbs energy from the sun, from other nearby stars, and it glows a little bit. That's why we see, if you're in a rural area in the dark, you see a tail behind the comet. That's just a glowing tail of dust, of gunk. It's sort of like how if you were to put a bunch of powder in the air and shine a light into it, you would see it. It's very similar. So comets glow because of the tail that's behind them. They glow because light's shining on it, the same way the ground, you can see the ground during the day when the sun's shining on it. But there are UV and IR emissions as well, infrared emissions. Like, whenever they use you see something from like a heat-seeking camera or an IR camera, people are usually red and yellow. They're really bright. You can't see that with your eyes, but they're putting off IR emission that's outside of the visible range. A lot of things put that off, comets included.
Right. And so, does a meteor glow? Technically, yes, but
does it glow in a wavelength we can see? Not necessarily.
Right.
All right. So thank you, Deborah. So the next one is Stephen from Facebook. What is your
Stephen from Facebook.
weirdest star facts?
Weirdest star fact. Okay.
Stars go.
Stars do explode. I think that's honestly the most interesting part of a star.
No, I've got one.
Okay, hit us.
Ashley, go to... Not yet, actually. Let me talk about it first. No, go to slide 6. So the light from a star comes from the core. All of the light we see comes from fusion in the core and fusion in the layers around the core. The fusion is, again, like I said earlier, it's called nucleosynthesis. It's whenever particles or nuclei collide and make bigger elements. Well, those collisions, those reactions, emit gamma rays. And those gamma rays are very high energy light. And they leave the core, and then they enter what's called the envelope. The envelope of the star is everything around the core. And particles in the envelope absorb those gamma rays. And they hold them for a little bit. Quantum mechanics says that anything can happen at any time. So those particles absorb the energy, and then at a random time, they spontaneously emit it. Sometimes it's a lower energy that they emit. So that light gets absorbed and emitted and absorbed and emitted, and it bounces all around the star. And I don't have the stream going, so I assume this slides up. If you see this slide, that's the path that one photon takes. Not any specific photon, but it's a possible path because it's random which direction they get emitted in. so it bounces around randomly for a very long time. Once the photon hits the outer edge of the star and starts heading to us, just as an example, from our star, it takes a photon 8 minutes. So light takes 8 minutes to get from the outer edge of our star to us. But when it's inside of the star, it can bounce around on average 100,000 to 1,000,000 years. That means that the light that hits us on average is 1,000,000 years and 8 minutes old. So what we're seeing now, what we're illuminating, what you're looking down and seeing yourself with, that light on average has been bouncing around trying to make it to you for 1,000,000 years. That's my favorite star fact.
No, I'll defer to that one. I mean, that's wild. It's pretty interesting to know, like, really, whenever you look at all the physics behind what's going on inside of these stars, what's going on in the process of the star evolving, how crazy it actually is. Like, what are you actually looking at is a lot older than you actually think. But yeah,
That's really cool. That's a really cool star fact that I didn't know. So thanks, Marcus, and thanks, Stephen, for asking that question. Next question is: when we see stars and associated planets, the images all seem to be "quote unquote" artist's conception. Um, when I do find actual telescope images, these are nearly invisible. Why the disconnect? From Eric on Facebook.
sure thing. Yeah, it's a good question, Eric. I mean,
Wait, I'm back. Repeat the question.
oh,
No.
if you go to the
No.
Google Doc, it's fifth one down there, my guy. But no, it's a good question, Eric. The true reason behind this is because when we actually do detect these planets, a lot of the times they are so small and so far away that we really only see them as variations of light. We don't actually see the physical planet itself, and very rarely do we actually physically see the planet through telescopes. But what we see is we look at the star itself, and the amount of light that it's emitting varies on a very regular basis that is attuned to a planet revolving around it. There's various ways of detecting planets, exoplanets, and potentially this could be one of our topics for a later Star Talk or one of these Ask an Astronomer things. But basically, the short answer to your question is none of the stars or none of the planets that you see in these artist conceptions, none of the planets that you see have been observed physically. Almost, I would say 99.99% of these planets have actually been detected through different means, whether it's through Doppler effect. We can see where the planet's pulling the star closer to us or when it's pulling it farther away. We can see that in the light of the star. Also, another way is, again, by these what we call transits, which is where the planet physically crosses in front of the star between like us and the star, which makes the star look a little bit dimmer because the planet is just blocking some of the light.
Yeah, hey, Ashley, I just added a new slide, slide 12, and this directly relates to what he's talking about. Can you pull that up?
Yeah.
Yeah, so and you know, this is where what I'm saying is like these different methods of us observing these stars, we can actually get a lot of information out of them. And the information that we're getting out of them is we can determine the size of these planets. We can also determine the size of the stars. We can do a lot of different things just simply with these kind of detection systems. And so then, depending on where we believe that they are and what size they are, we can determine if they are inside of the habitable zone. And if they're inside the habitable zone, then we know that water could exist on that planet. And then artists go crazy. And there we are. We get a lot of these pretty pictures, and it's not exactly what we'll see in real life. But nonetheless, it's still very interesting in terms of the possibilities out there.
So to explain this figure I just put up, this is what we call a light curve. And a light curve is actually directly related to a paper I'm writing right now, is over a period of time, the amount of flux, and flux is the amount of light per area. So it's the amount of light we're getting, and on certain days, we take a measurement every so many days, and if you look here, around day 1, there's a huge dip, and then around the middle of day 3, there's a huge dip, and around the middle of day 5, there's a huge dip. That's when we would consider. Now, timescale of days is very small and not realistic, but it's similar to a planet orbiting that star. So if instead of days we consider it to be years, after around 1 year it orbits. Then after about 3.5 years it orbits. And after about 5.5 years it's in orbit. It's crossing our plane of view with that star. And based on how wide this dip is, and whenever we look at the type of light that we're seeing at that time, what we call the spectrum, we can determine what elements compose the thing that's blocking the star, and we can figure out how big the planet is. Whenever we know what elements compose it, we know if it would be a habitable planet or not. So if it has things like methane or ethyl alcohols in it, probably not a habitable atmosphere. But if we see a lot of nitrogen and oxygen and carbon, it would probably be a habitable planet, because it's a place where those elements can exist in their basic diatomic forms in the atmospheres of the planets. So whenever we look for if a planet is habitable, we look for these transits to figure out the size, because if they're too big, then the gravity is too strong to sustain life. But if they're within 1 to 2, 3 at the most Earth sizes, or a little bit less, and we see significant carbon, nitrogen, oxygen from that family of elements in there, then it might be habitable. But there's a lot of factors that go into play. If you're really interested, look up the Drake equation. The Drake equation is a very widely known equation that basically accounts for everything that's necessary for life and the probability of finding it in one planet around one star. But as I said earlier, I didn't hear the question, but that's everything I have to say about finding exoplanets with transit orbit.
Well, yeah, and you know what? We'll go over exoplanets a little bit more later too. I think that'd be a good topic for later for sure. But yeah, no, let's go ahead and move on. I think we kind of covered that one pretty well. And if you do have any more questions, please go ahead and throw them in the chat.
All right.
By the way, I might have accidentally stolen this cup from a Pizza Hut. I don't remember. I don't know where it came from, but you can't just buy these.
Right.
Anyway, not a sponsor.
It's a collectible now. All right. So the next one is, do all stars have the same kind of core, or what are those kind of cores? From Heidi, Facebook.
No, it's a good question, Heidi. And the answer to your question really depends on what stage of life it's at. In the majority of its stage of life, a star will have a core that's hydrogen fusing into helium. And that is 100% the core. It will just be fusing hydrogen to helium, hydrogen to helium, hydrogen to helium. And that process takes, like we mentioned a little bit before, it takes a very long time to actually burn up all of its reserves. Once it gets past that point, it will then start really rapidly using the rest of its elements until it gets to iron. And depending on the mass of the star, there's a few different options that will actually occur. It could become a neutron star. It could fall into a white dwarf. And if I'm not mistaken, it can also just collapse into a black hole. So
before we go into the end of the life, I want to focus just a little bit on what you said right before that. I didn't mean to interrupt you, Cooper. I'm sorry.
No,
I didn't want to skip over this. Ashley, can you pull up slide 10? So the core in the beginning, when the star is young, fuses hydrogen into helium. And then you go out a layer and it fuses heliums into nitrogen, and then nitrogen into carbon. So there's two main paths that stars take on their fusion journey. Smaller stars follow what's called the PP chain. And it's okay to laugh at that because I do every time, because I'm 12 years old. The PP chain is when protons and protons collide and fuse into hydrogen and then helium. The PP chain is what, like I said, what smaller stars follow that releases gamma rays and neutrinos. Particle physics and fusion, that'll be another week's topic. We'll go a lot more into that. But once it fuses all of the hydrogen in the core, then it starts fusing helium. But right outside of the core, there's some hydrogen left. So right outside of the core, it'll start fusing hydrogen. But then that area right outside will run out of hydrogen. So it'll start fusing helium. But then that area right outside of that layer has some hydrogen left. So it'll start fusing. And that keeps happening all the way out. And those inner layers will start fusing heavier and heavier elements. So if you look at this figure we have up, you'll see at the core there, it's fusing iron and nickel. And then the next layer, selenium and sulfur, and then oxygen, neon, and magnesium, and then oxygen and carbon, and so on. So the heavier elements are fusing in the center, but those outer layers are fusing lighter and lighter elements. So eventually, you'll get to iron and nickel in the core, and then you just lose the efficiency of fusion at that point. And in bigger, heavier stars that will make it to iron, some won't. But if they're big enough to make it to iron, then you can pull up slide 2 now, Ashley. As Cooper was saying, there's a few different paths the stars can take. And there are limits on mass as well. Like we have pretty well-defined limits on what the mass has to be for these different stages of end life to happen. Cooper, you are welcome to butt in at any moment. So if you look at the top of this figure, it says the average star. Ours is considered an average star, a red or a yellow star. It'll go through its life, it'll burn up its fuel, and then eventually the radiation pressure from burning heavier elements will outweigh the gravitational forces, and it'll grow into a red giant. Then eventually the radiation pressure will be so strong that it'll beat the gravitational forces, and it'll turn to a nebula. And a nebula is where the core falls into a white dwarf, and the stellar envelope, which is just the gases around it, will just kind of dissipate and create the beautiful planetary nebula you see in this picture. Most of the really pretty things you see in space, all the different colors and the big structures of gas and clouds, those are nebulae. Those are dead stars. So whenever that gas dissipates, it'll leave behind a white dwarf. And that white dwarf is held in equilibrium by what's called electron degeneracy. Again, we will talk about that in depth in when we eventually do particle physics. But electron degeneracy is basically when everything is so compact and so pressurized that quantum mechanics does not allow electrons to occupy the same energy states. So it's kept big. It's kept the shape that it is.
Right.
You just fall into it's the exploitation of the Pauli exclusion principle, which is saying that electrons cannot occupy the same spaces or energy states, so they're just kept out here based on a fundamental law of physics. That's the bottom level. It's a law of physics we cannot break. Whereas the bottom row, you see this massive star turns into a red supergiant, but the gravitational force in this case wins, and it collapses. Rather than being pushed out and dissipating, it all falls into the center and goes, and then that pop has two possible end games, outcomes. And that again depends on the mass. So here we talk about what's called the Chandrasekhar limit. And that is where you move from a white dwarf to a neutron star. That's wrong. I'm sorry. I'll talk about the Chandrasekhar limit next. Hold on. So between, I want to say 5 and 8 solar masses, which means 5 to 8 times the mass of the sun, you'll get a neutron star. And a neutron star, again, is fueled by electron degeneracy pressure, which, again, we will define much more in depth later on, a different week. A neutron star is where all of the electrons and protons have merged and neutralized each other, and it's actually just a very fast rotating star full of neutrons. If it's a little bit heavier, say 8 solar masses or above, you got a black hole. And a black hole is what we call a singularity, which is where all of the mass falls into a singular point, and the gravity is so strong that nothing can escape it. And we will have another week specifically about black holes.
Right. Black holes are much more of a long-term chat, because that's in and of itself quite a topic.
So these are the three main paths that a star can take.
Right.
Right. So, what about other stars? Other stars? Let's say we did have a pretty good representation of the layers of, like, say, our sun. Like, if this were to happen to our sun, what about do all stars look like that? Their cores, or maybe something like a neutron star, something different. Is that different?
Neutron.
Right.
Go ahead, Cooper.
Well, so a neutron star is more or less a result of a star's life, for lack of a better term. It is basically the end point of what we would, I guess, call a normal star's life. Where a normal star, again, is where we basically define as anything that's burning hydrogen to helium at its core. And once it's completed that process, and I believe we just showed on that last one, where with the life cycle of a star, a neutron star is more of the end game, and we can talk a lot more about those end games maybe when we do black holes and end games of stars. But
definitely, yeah, you'll definitely have to stay tuned to that.
They're very interesting objects, just because they're very unique remnants of what has happened post supernovae, which have unique features in it of themselves. And I believe those are actually the very, very dense objects that we've actually observed in LIGO with gravitational waves. We've observed these objects colliding with one another whenever they're extremely massive, and they can actually affect the space-time fabric, which we'll have to get into a whole nother day. But nonetheless, it's a very good question about the cores of stars, for sure. Thank you, Heidi, for that one.
All right. So the next question is from Eric. He asked, easiest way to see cosmic rail trays at home.
Cosmic ray trails
at home.
Rays.
Okay.
Well,
okay, go ahead.
So our interaction with cosmic rays is they are a plague on us, because whenever we observe things with telescopes, we observe in very specific bands, which means very specific wavelengths. And for Cooper and myself, we're both currently working in the infrared, which is a very low energy wave. But then a cosmic ray, if it happens to just appear in our observation, those are significantly higher energy. And if you're observing in radio or infrared, cosmic rays can ruin your observation. So cosmic rays have to be accounted for, and a lot of the times we have to apply mathematical models and normalization programs. We have to apply these algorithms to our observations we're working on just to get rid of them, because they can make really bright spots, they can obscure our data, they can be a real plague on us. As far as observing them at home, you can, there are multiple gamma ray and cosmic ray surveys you can look up online and just look at the observations. Cosmic rays are a lot rarer than the normal things we observe, because they are typically.
I'm gonna throw a quick thing in here. And I will say this: at home, there's ways that you can make kind of like an at-home cosmic ray detector. You can't necessarily say, "Hey, there it is, right there," and point at it, but you can detect the presence of a cosmic ray. In fact, in my senior year of undergrad, we actually did a process where we basically set up hydrogen tubes, and we ionized hydrogen. Not hydrogen, helium. We ionized helium, and as cosmic rays would pass through this ionized helium, it would interact with it, setting off a spike in the voltage of our tubes, And as long as you can measure the voltage in those tubes, you could measure when a cosmic ray passed through. So actually, they pass through more often than you think. But nonetheless, like Marcus was saying, in general astronomy, most of the time they're kind of plagues on what we're looking at. But yeah, no, they're usually pretty intense in terms of light speak. But yeah, to be 1,000% honest, saying easiest way to see them at home, unless you fashion yourself a cosmic ray detector, which there are some schematics for that online. It's a little bit tough, but nonetheless, you could still do it.
All right, we're running low on time. Let's rapid fire these next questions.
Yeah,
Sure
but
thing.
remember, we also started late, so we can go a little bit over time, too. So that was our bad. Or my bad, really. I'm going to blame myself on that. So, next question is, easiest... no, we answered that one. The next one is, what are the detection machines for light zones, kind, and locations of the measuring machines? From Eric.
What?
I'm not entirely sure if I quite understand the question, but let me try to kind of dissect it. So what I'm looking at here is detection machines for light zones.
I think it means different regions of the EM spectrum.
Oh.
Right. Right. I think maybe what he's referring to is, and please feel free to correct us if we're off the beaten path. But what we're looking at is basically whenever light comes in, right? In a similar way to biologists will dissect a frog and they'll look at all the insides of it, right? What we do is we dissect light. And light goes from, in the optical sense, it goes from red to blue. However, it actually extends much farther beyond that in both directions. They go into the ultraviolet, which is beyond blue, and they also go into the infrared, which is beyond red, and even further than that, but that's the closest to us. Depending on the detector you have, and depending on a lot of times we'll use diffraction gratings, which diffraction gratings are just a fancy way of saying the scalpel that cuts open the light. That's essentially what a diffraction grating does. It cuts open the light so that way it opens up and we can see all the different wavelengths that it has. And then we can then study those wavelengths. Even though we can't physically see the infrared light, even though we can't physically see the UV light with our own eyes, we can still study that light that comes off of the stars. And that's really a big way that we're able to see those kind of things. And usually all of that is done on major telescopes, rather sent out into space, oftentimes on mountains. There's a few spots in Hawaii, there's a few spots on Chile, and various spots in Europe. I'm not entirely positive about the Europe sites, but I do know Chile, Hawaii are pretty prominent ones for the full-time astronomy. Normal astronomy, we can still do that same exact thing, just you have to get a diffraction grating in order to slice open the light.
Yeah, he meant, I guess, detecting different elements of stars. So maybe it's more of a spectroscopy he's talking about.
Okay, yeah, no doubt. With spectroscopy, really what the thing is there is each element spits out a specific wavelength of light. So again, when we dissect light, when we cut it open, each element will have its own unique look, will have its own unique signature, will have its own unique fingerprint, per se, on the light spectrum, which is basically just cut open light. And based off of what we see from that cut open light, we can determine, okay, well, there must be gold here, there must be silver here, because silver and gold leave very specific fingerprints on light. And so when we look at that light and we see those fingerprints, we then conclude, okay, well, it must have had those particular elements. And each element has that in its own, which is actually where we determined that we had helium in the sun. Helium was actually first discovered in the sun, which you can kind of infer from its own name, because it's called helium off of Helios, which is I think it's Greek for the sun, and we first discovered that there because we saw the fingerprint and we said, hey, what's this fingerprint doing here? And later on, we discovered that that was actually helium. So, no, it's a really great question. There's a lot of stuff that goes into it. And spectroscopy itself has a very deep and rich history that maybe we'll get into in full depth on a future Ask an Astronomer, for sure.
So it's currently 6 o'clock, which is when we're supposed to end. But speaking for myself, I have nowhere to be. So if questions keep coming, I'm okay keeping on going. Ashley and Cooper, are you cool with that?
Yeah, I'm fine. Cooper?
Yeah, I've got a bit in me.
Okay, because technically we've only been on for about 15 minutes, so we really, if we're going to do an hour, we still have 10 more minutes.
All right, let's go. What's next?
Okay, so the next one is are neutron stars' layers a lot like the layers of the Earth? I think she asked this when we were talking about the layers of the sun. This is from Anne.
Okay, yeah. So in the sense of, I kind of lost you there, Ashley.
Oh, you can hear me?
But
did you hear the question, Cooper?
I'm just going to continue talking.
Cooper, did you hear?
But regardless, I think
Cooper, can you hear me, Cooper?
the question kind of arises whenever we are looking at that
Oh no!
image
Lost
of
him.
the inside of the neutron star.
Cooper!
Am I gone?
Cooper!
I don't know. We see him.
Am I completely gone?
No.
Hopefully not. Okay. Is Marcus just freaking out? Naturally.
Cooper!
Can you not hear us?
I can hear Marcus screaming my name a lot.
Oh, hey, Cooper.
Hi, I'm Marcus.
Okay, can you hear me?
Did you hear the question?
Yeah, okay, I'm back. I think so.
Did you hear the question?
I did.
Okay, go.
Yeah, no, well, I was saying this probably comes a lot from the image that we had earlier that was inside of a neutron star, where it does look like the crust, like the core, the mantle, the crust of Earth. And absolutely, it does have layers, because essentially all of these stars or neutron stars will have those layers. But despite that, these layers are going to be far different than what we see inside of Earth. In Earth, at the center of Earth, we're going to have that molten, the kind of lava core, where it's that molten iron, because that's what we've gone up to. But in the inner core of neutron stars, we have no idea what it is, but we know that based off of its density, it has to be extremely, extremely dense. And in fact, so it's going to be so compact in there and so energetic in there that it's possible that neutrons and protons don't actually come together to actually even form hydrogen. I mean, the pressure there is so great that they can't come together. And Marcus, I don't know if you have any comments on neutron stars in general, but also my dog is going to now join the party.
Oh, hi, Luna. I honestly stepped out of the room and I did not hear everything you said. But neutron stars.
Cooper did a good job in answering.
Good job, Cooper.
Right.
But what it comes down to, neutron stars, they are neutral. Protons and electrons have neutralized each other, and the outer layers are just a bunch of neutral elements, free electrons floating around because there are more electrons. And we don't know about the inside. They're too small. We can't see that far.
Right.
All right. Next question is: are nebulae that we see in photos from telescopes made up of more than just one neutron star?
Okay, so usually planetary nebulae, what we're actually seeing is a white dwarf. Actually, that's I believe, as we had the remnant up there earlier. A white dwarf is generally a smaller star that has fused all of its stuff, and then it blew off its outer layer, and so then we'll see this nebulae that's a result of that. Now, there's multiple different types of nebulae that we can see, but for planetary nebulae, which are a little bit confusing, planetary nebulae are actually results of stars that have exploded and blown out their outer core. Not necessarily exploded because we didn't necessarily get a supernova, but it did blow out its outer portion. And what's left at the center is just a white hot white dwarf, and then the surrounding gases. And those surrounding gases is where you get your pretty colors. And like Marcus was saying earlier, I'm sure you guys have seen some of those pictures that are real pretty, that have these, you know, gorgeous images, and there's like a white dot at the center. And to answer the question as best as I can't think of off the top of my head a situation where we've had more than one white dwarf at the center of these stars. Not to say that it doesn't exist, but off the top of my head, I can't think of one.
Same. About the shout outs. Hi, Johnny.
Huh, nice. Yeah, I saw the GIF that we posted.
There's a GIF? Yeah.
You'll have to check it out. So let's see. I know we have another one. Thanks, Eric. He said this is way better than news articles on astronomy. I totally agree. Live interacting is way more fun. Let's see.
Bunkus.
I think we're good. I think we answered their questions. Let me check. Sky Theater.
Caroline, the GIF. Hi, Carol.
Yes, we did answer all the live questions.
Great.
Was there something from the Google Docs? Maybe one more question from the Google Docs?
Let me see if we had any more slides that we wanted to talk about.
Yeah.
We can talk about binary systems.
Sure.
Yeah, I added that slide in because I thought that was super interesting, binary star systems. Because I just recently learned that not only can there be 4 stars in a system, but there can be up to 8 stars in a system. That is so cool. So let me just pull that up.
Spaghetti. Stars. So yeah, there's actually a star in.
Nope.
Ursa
No.
Minor?
Oh wait, do we have that? Do we have that slide?
Which one?
I thought I added a slide about multiple star systems.
I don't think you added one, but we had
No.
we had one.
All right.
Maybe
All right.
you had one. You didn't put it in the slideshow.
I'll find it. I'll find it. Okay, you answer the question.
There's a star in. It's either Ursa Minor or Ursa Major. I can't remember right now. But it's like the second star from the bottom of the handle in the bigger Little Dipper. If you look at it with binoculars, like that, it appears as a binary system. But if you look at it with a telescope, it's actually, and some people think, no one's really sure, it looks like a binary system orbiting a quadruple star system, which could be considered a 6-star system. But there can exist more. It depends on just chance of them moving through space and matching each other's orbits.
Sure, and actually, what's just kind of like a random fun fact for the day, there's various binary systems in our observable universe that have been around for a long time, and a lot of times back in the way back in the day, like in the Roman times even, they would actually enlist people into the army based off of your ability to see these binary stars, where most people might only see single stars, and they would actually they could see 2 separate stars, or if it wasn't binary stars, then it was double stars, which are also a similar thing, where instead of them actually being orbiting around one another, they're just both along our line of sight.
Mm-hmm. An example of that, so the top of Orion and the bottom of Orion, that's Rigel and Betelgeuse. One's red, one's blue. And whenever you look at a constellation, it looks like all the stars are the same distance away from us in a pattern. But Rigel, the blue star, is actually twice as far away as Betelgeuse. They just appear the same size because Rigel's a big, bright blue star, and Betelgeuse is a smaller, redder star, closer to us. So stars can be significantly different distances, but look like they're the same distance away based on relative size, which, if they're close enough together spatially or linear, I don't know how to describe that. They could look like a double star system, but they actually aren't. Or they look like a binary star system, but they're actually double stars. Did you find a slide, Ashley?
Yeah, I put it up. It's just a binary star orbit and kind of like what that looks like. I'm going to post a link to a YouTube video. It's he's a creator called Astronomer, and he has the most amazing astronomy videos. And he came out with a really informative, like video about all about star systems. So I'm gonna post that link in the chat. If you guys want to talk about maybe one more slide, and we'll be good.
Yeah, so a quick thing about binary star orbits. Most people think that there's a really big star and then a star orbiting it. But that's not necessarily the case. There's a center of mass between the two. So if you look at the slide she put up, you see a center of mass just to the right of the blue star. Both stars are orbiting that center. So it's not one star orbiting the other. It's the two stars orbiting that center of mass. And sometimes mass from the lower mass star is falling into the mass of the larger mass star, which I think we saw on a slide earlier. I don't remember if we showed it. Do we have any more questions?
No more questions.
Well, and if you guys do have questions, of course, you're more than welcome to leave them, and we'll get to them next week. I believe next week we do have a poll up to talk about whether it's going to be cosmology or particle physics. I think that's what it is. Or did we already decide that?
No, we haven't decided. It's a poll. But just to define those two terms, cosmology, for those of you that don't know, is the study of the early universe. So basically, we look back in time to study the effects and the state of the universe around the time of the Big Bang. And if we do cosmology, we can talk about how the Big Bang is actually an inaccurate name for it. And particle physics is atomic physics. It's the physics of subatomic particles and their interactions, their dynamics. A lot of really, it sounds boring, but there's a lot of really interesting stuff in particle physics. And a lot of astronomy too.
With both of these, they have very interesting subjects. And, of course, we always appreciate anybody who comes out, wants to watch these streams, ask questions, interact with us. Really, like, we might not have all the answers, but we're going to give it our best go.
All right. Wait, I think we have one more question.
Sure.
At least Cade said that we did. Hold on. Let me look.
Roger.
Can you talk about the primordial black hole theorized to be orbiting our solar system?
Well, let's talk about the word primordial real quick. That means, primordial means to be existing at the beginning of time. So if something were to be truly primordial, it means it would have existed at the initial inflation, like right when the universe started. So I don't think we can necessarily have a primordial black hole because that does take time for the mass to collapse. But there are lots of proposed smaller stellar mass black holes orbiting around our solar system. I'm sorry, no, not our solar system, our galaxy.
Galaxy.
Yeah, there's a bunch of stellar mass black holes because any star over 8 solar masses that explodes is likely going to fall into a black hole. So there are lots of those, and if those happen to be around planets or a gas cloud, they can form into what we call microquasars, which do exist on our solar system, which are black holes with accretion disks and small jets. As far as a primordial black hole, I don't think that that is something that can theoretically exist.
Well, and I think this kind of stems from the images that we've seen last year. That I believe that came out last year. That were the images of the black holes, and now the reason why we even theorized for them to exist in the first place is because we've observed objects around the center of our galaxy, not solar system here, But when we observe the motions of the objects around our galaxy towards the center, we see them have these orbits that are only conducive to an extremely, extremely dense object at the very center. And this is why we theorize that there's a black hole there, because no object can have this kind of mass in this small of area and sustain itself. So this is a really good question, and I think full description we should probably postpone until full black hole discussion, because black holes in it of themselves have a ton of information that they give us, have also a ton of questions that they give us, because we truly don't know everything about black holes, but nonetheless they are very interesting. Also, okay.
And if we end up doing the cosmology talk next week, inevitably black holes will come out of that. And
for sure.
Black holes, while very simple systems, most of them contain just mass, charge, and angular momentum. They tell us a phenomenal amount about the galaxy around them. So I'm really excited to talk about black holes. I think that's it for this week.
I agree.
Yeah, I think so. We did have a lot. I feel like we had a lot more questions today than we did last week, and hopefully the stream wasn't really laggy or freezing. We did have some difficulties at the end, which kind of pushed the stream back about 10 minutes or so. But I think we're going to regularly do the Ask Astronomy here in the planetarium. There's one thing I didn't mention at the beginning, because I wanted to get these questions rolling out, is about our donations. If we are still accepting donations, and I believe Cade put a link in the comments, we are still sending meteorites out to people who donate $50 or more. I have those meteorites in my possession, so I think, yeah, so I'll be sending those out. I get a list of people and I'll send them out to you guys. If you can't donate anything at all, thanks Marcus. If you can't donate anything at all, just like and share our videos with people, your friends and family, or people who love space in general. I believe that is it. There's just so much to keep track of. I think we covered everything. But thanks a lot, guys, for joining us. And if we didn't answer, I think we answered all the questions, but we didn't, we'll just make sure and we'll go back in a little later and we'll reply to you. But I think that is all from us, and you guys have a good day.
Yeah, if we missed your question or comment, please send us an angry, nasty email. We really like those. So keep them coming, guys. Thanks.
Yeah.
Yeah. To Marcus Thomas at UNT.
Marcus Thomas at my.unt.edu.
There you go. Send it that way.
Or fax it. I'll get to it eventually.